Okay, so this is where we stopped. Talking about Lewis structures, this just describes the shapes of molecules. It just helps you to describe the shapes of molecules. And to get Lewis structures, the only electrons we are interested in are the valence electrons. Okay, just to refresh your mind, valence electrons are electrons that are in the outermost shell. Yeah, valence electrons are the electrons in the highest energy shell of orbitals. Okay. Well, let me give you an example to remind you what valence electrons are. For example, carbon has atomic number of 6. So the electronic configuration of carbon with atomic number 6, with 6 electrons, that is, the atomic number equals to number of electrons, gonna be 1s2, 2s2, and then 2p2. That gives you the 6 electrons, 2 plus 2 plus 2. The outermost shell is the second energy level, right? So that's the principal number 2. So we circle the second shell and then sum up the number of electrons in it, 2 plus 2, so it's 4. And that's why carbon is in the fourth main group. That's why carbon is a fourth main group element. And it's right here. That 4 just that tells you that we have 4 valent electrons in the outermost shell, and that's why you have the 4 dots. Now, using the valence electrons that are shown on this periodic table, just like you have those dots, we're going to draw Lewis structures. Okay, so the next slide just kind of explains to you what an anion is, what a cation is. And you have two types of bonds, the ionic and covalent bonding. In ionic bonding is usually again between a non-metal, a metal. Sodium here again is a metal, and this is a non-metal. So you expect the bond in there to be ionic, and it's characterized by complete electron transfer. In covalent bond, you get sharing of electrons. Okay, so, and again, we can base the type of bond based on what we call electronegativity, and we're going to define electronegativity, which is just the affinity of electrons by an atom. Okay, this is the measure of force of an atom's attraction of electrons, which are shared between itself and another atom. So it's the affinity of electrons by an atom. All right, so the more electronegative the atom is of an element, the more mean it is, the more it's going to attract electrons towards itself between a bond. Okay, so if an atom is electronegative, that means it's have a high affinity for electrons. It wants those electrons, and the electronegativity generally increases across the periodic table and up the periodic table. So that tells you that fluorine here is the most electronegative across the periodic table. Group 8 elements here are not shown. Why? Because they don't gain, they don't lose electrons, so we don't show them here. All right, so going across, fluorine is going to be the most electronegative. Going up, still fluorine is the most electronegative. All right, so there's a guy called Pauling who developed numbers, a number scale for electronegativity. He gave the values. The numbers that you see in the periodic table, the higher the number, the more the electronegative. You see fluorine has a 4.0 Pauling scale value, so it's most electronegative according to the list that we have here. But keep in mind, you could have these two elements having the same Pauling scale number, like nitrogen and chlorine. So there, the Pauling scale is not going to help you. Or carbon and sulfur, they have the same Pauling number. So there, it doesn't help you. You really want to use in that case, going across and going up method to determine which one is more electronegative. But where the numbers are different, you can go ahead and use the polling scale. Usually I provide you with this chart in the test, so you don't need to memorize the numbers. This is usually provided in the last page of the exam. And then you apply this with the formula to determine the type of bond, whether it's ionic or covalent, and that's what you're going to do next. So if you do the subtraction between two atoms and you find the answer is less than 5, then you're looking at a nonpolar covalent bond. If the number is, the difference between the electronegativity numbers values 0.5 to 1.9, you're looking at a polar covalent. That means they're sharing, and usually you see that between two nonmetals or between a nonmetal and a metalloid. What's a metalloid? Metalloids are elements in the periodic table. I think this line across, that's the elements sitting up there are metalloids, that they don't behave like metals, they don't behave like nonmetals. Okay, if the difference in the polling scale numbers is greater than 1.9, then you're looking at an ionic bond. And ionic bond, as I say, is formed between a metal and a nonmetal. Okay, these ranges are just arbitrarily, or you would say they're made up. Sometimes we need more classifications to determine the type of bond. Like I said, where you have similar polling scale numbers between two atoms you're comparing, then you can decide the type of bond. But most likely you're going to be looking at a covalent bond. Alright, so what type of bond is between H and O in water? Now, again, you're going to use this table that's going to be provided in the test. You're simply lifting number values from the table and inserting it and doing the difference, get the difference, and then use this little chart here to answer. This chart table is not provided in the exam, not provided. You have to memorize it. This is one of the few things you need to memorize in this class. This is not provided in exam. Okay. Alright, so let's work on this. So hydrogen obviously has a 2.1 scale, and then oxygen has a oxygen is right here. It has a 3.5 scale, polling scale number value. You do the subtraction, you get 1.4, but according to our chart, according to our little chart here, 1.4 is going to be in between 0.5 and 1.9, so that means you're looking at a polar covalent bond, and that's why H2O is a polar solvent. That's why water is a polar solvent. Okay, so you're looking at a polar covalent because that answer lies between 0.5 and 1.9, which characterizes a polar covalent bond. Okay. Alright, for HCl, the type of bond that you're looking at here, again, H, hydrogen has a 2.1 scale, polling scale number, electronegativity number value, and chlorine has a 3.0 polling scale. So you do the subtraction, 0.9, and 0.9 lies between 0.5 and 1.9 again in the little table in the previous slide that I told you have to memorize. That means you're looking at a polar covalent bond. Okay, you have to practice this because it's gonna might show up in the quiz or the test, whichever comes first. Alright, in KBr, the potassium bromide, again insert the number value for potassium. The polling scale is 0.8, and for bromine is 2.8 according to this polling scale periodic table. The difference is 2.0, and it's above 1.9, and we know greater than 1.9 is ionic according to the table in the previous slide. So that means the bond in here is an ionic bond, and so forth and so forth. So what type of bonds are in the following compound? You do your math, you should find that between oxygen and sodium is completely ionic, the difference 2.6. Each of these single bonds between the carbon, here you have a carbon by the way, where you have a corner that's a carbon. Between the carbon and the oxygen, you will find it's going to be 1.0 for both sides. Here to oxygen, carbon to oxygen single bond, carbon to oxygen double bond. Looking at each of those bonds in the double bond singly, you're going to find their polar covalent. And of course, between carbon and hydrogen is 2.5 minus 2.1. The answer is 0.4 is less than 0.5. You're looking at non-polar covalent bond. Alright, so this guy can be drawn and blown up to be drawn like this. Okay, it's just the same thing. Sodium acetate. Here is the sodium acetate molecular formula. This is the sodium acetate open structural formula. In fact, this is the Lewis structure that we'll be drawing. We'll be drawing in a moment. So this is the Lewis structure, okay? Alright, between carbon and carbon, that's what we're looking at here. Of course, it's 2.5 minus 2.5 Pauling scale value. The answer is 0. You're looking at less than 0.5 again. So the type of bond here is non-polar covalent bond. So sodium acetate contains both ionic and covalent bonds, and usually ionic character trumps covalent character. So overall, the sodium acetate is an ionic compound, which means if you drop it in water, it's going to dissolve right away. It's highly soluble, right? Sodium acetate is an ionic, an organic ionic compound, just because one of the sites has an ionic character that makes overall the whole compound to be ionic. So how do we form an ionic bond? Ionic bond is formed when you have complete electron transfer. The atomic number for sodium is 11, so Z is equals to 11. Z represents atomic number. The electronic configuration will be 1s2, 2s2, 2p6, 3s1. So I told you a bond is formed involving valence electrons, and that's how we usually do our Lewis structures also. So now the outermost shell or energy level in sodium is going to be the 3. The third energy level, it only has one electron, one valent electron. And in fluorine, which has atomic number of 9, the electron configuration is 1s2, 2s2, 2p5. The valent electrons are 7. That's why fluorine is in group 7. And in the outermost shell, the 2s2 is full up, but the p is missing one electron. So you can imagine it's easy for sodium to lose the one electron and gain 7 to be octet state, and it's easy for the fluorine to gain one electron to fill up the p orbital to make the 7 to be 8 electrons, which is an octet state. So in this case, we're going to have a complete transfer of an electron. Now I'm using a fishhook arrow because you're moving one electron. In the future for this class, you mostly be using a double-ended arrow to show two electron movement. But in this case, you are moving one electron, so we use a fishhook arrow. We call it a fishhook arrow in organic chemistry. And so down here, since we have one valent electron sodium, we're just representing it as a dot, and this fluorine has 7 valent electrons, so we present those 7 dots, and we are pairing up the lonely electron in the valent in the second shell of electronic configuration of fluorine. We are pairing that electron with an electron from sodium. You see, there is a complete transfer, right? So there's complete electron transfer. And because you're transferring the electron from sodium to fluorine, sodium becomes positively charged, and that's how you form a cation. And fluorine becomes negatively charged, so it becomes an anion. We'll explain later the effect of this positive charge and negative charge in Lewis structures. Alright, ionic bonds end up forming ions, sodium ion and fluorine ion. So this is a sodium cation and fluoride anion. And of course you see there's no really bond that we've drawn here. That tells you that this is the kind of bonds you're getting here is electrostatic, and it's an ionic bond that would be expected to be formed, but we really don't show it because these ions are floating around freely in solution. Alright, so if you are to draw the circle representation of electronic configuration of sodium, this is how you'll see it, but in this case we are not doing sodium and fluorine, we are pairing up sodium and chlorine instead of fluorine. So again, the valent electron is transferred to the lonely, that's why it's called a lone electron, to the lonely electron in chlorine. This is the electronic configuration of chlorine, of course. And then that's the red one, the red electron that was transferred from sodium. So sodium becomes Na plus, chlorine becomes Cl minus. Alright? So this again is a cation, is positively charged, chlorine is an anion, negatively charged. That's how you get sodium chloride, which is in table salt. For covalent bond, you have to have sharing, so there is sharing of electrons. So no one loses, no one gains, it's shared. Just like if you want to buy a burger and the burger costs $5 and you have $2.50, if you want to say, and your friend has $2.50. So you just add the two currencies up to make $5. You buy the burger and split it into two, and both of you are happy, right? You eat and your tummy is full, right? You just share it up. So that's how you form a covalent bond. Right? You slice your sandwich into half, and each one of you is happy. So hydrogen in itself has one atomic number of 1, so you only have one valent electron in the 1s shell. So you're going to share them up. Again, we're using fish hook arrows because you're moving one electron, and you're going to form a bond. By the way, a bond is formed by 2 electrons. So these 2 electrons that are shared forms a bond. Keep that in mind. Very, very important. A bond is formed by 2 electrons. Each time you have a bond, think 2 electrons in there, right? Now, this reaction of joining 2 hydrogen atoms usually releases energy. That's why this is a negative sign here. Tells you the reaction is exothermic. And for this type of reaction, you lose 435 kilojoules per mole, or negative 104 kilocalories per mole is lost to the environment. So the reaction is exothermic. That's the relevance of that sign. If this was positive, then the reaction would be endothermic, heat added to the reaction. But here heat is lost from the reaction, so it's exothermic. Alright, so usually there are symbols that we use to show electronegativity or to show polarity in a molecule. The pointer of the arrow will point the atom in the structure which is more electronegative. Now from the Pauling scale, you know chlorine has a greater Pauling scale number value than hydrogen, so chlorine is more electronegative. So the arrow should point towards the chlorine. Now this slashed arrow just represents dipole moments. That tells you chlorine is more electronegative than hydrogen. Now remember, I told you a bond is formed by 2 electrons, right? So if chlorine is more electronegative, then the electron cloud caused by the 2 electrons in the bond will be closer to the chlorine than to the hydrogen. And that's why HCl is acidic, because this bond is not really bonded to the hydrogen. The hydrogen can easily be lost. And you know acids are proton donors. We'll talk about that in chapter 2. Alright, so chlorine has a high affinity for the electrons, and that's what we call electronegativity. So the dipole moment should point towards the chlorine because chlorine is more electronegative. That makes HCl polar. because of the large difference between the hydrogen and the chlorine in terms of electronegativity. If you do the math using Pauling scale, you'll find that the bond in between here, the difference between H and Cl is kind of higher, so you get a polar covalent bond. All right. Now, in ammonia, nitrogen is more electronegative than hydrogen. Of course, going across the periodic table, nitrogen is farther to the right. So nitrogen is more electronegative than hydrogen. So again, the dipole moment should point towards the nitrogen. Okay? And because the electrons are spending more time towards the chlorine here than the hydrogen, chlorine will be partially negative, electrons are negatively charged, and hydrogen will be partially positive. Alright, now same thing here. The electrons want to spend more time towards nitrogen than the hydrogen, so hydrogen will be partially positive, the nitrogen will be partially negative because of a higher electron cloud close to nitrogen than the hydrogen. So again, these arrows are called dipole moments, and that makes ammonia very polar because, of course, these dipole moments are oriented towards the nitrogen than the hydrogen. And it's polar again because you have partial negative charge on top and partial positive charges at the bottom. So you see, you create a dispersion of charge, and that makes it polar, makes the whole ammonia molecule polar. Alright, now to switch gears, we need to know how to draw Lewis structures based on the valence electrons. So these are just steps that are followed, general rules that are followed in drawing the 3D structures or 2D structures of representation of atoms. Remember, like in the last slide, ammonia is drawn like this. Why is it drawn like this and not just like this, like sitting on the surface of your desk? Because right now this one is said to be trigonal pyramidal because it's 3D. Well, of course, this is trigonal planar. This is wrong. So why is this correct? We're going to explain that using Lewis structures, following Lewis structures, rules and steps. Now, if you have hydrogens and halogens, always put them outside the structure. Like in ammonia, you see the hydrogens are put outside. And usually molecules tend to be symmetrical. You want to get some symmetry, and that's why nitrogen is drawn in the middle and hydrogens are outside. And then you have to calculate the total number of electrons. But I want you to include in your notes that not all electrons you're looking at valence electrons, the electrons that are well outside, like valence electrons. Those are the ones that are summed up. Alright, so allow me just to go and start working on examples rather than reading all these statements here, but whatever example I'll be working on will be following these 3 steps. It's easier when I explain the steps while working on a problem than just reading a lot of text. You guys know how to read. Now, I told you you're looking for symmetry. So what's the Lewis structure of carbon monoxide, like in this example? What's the Lewis structure? So step 1, you want to write your elements looking for symmetry, but because here you only have 2 atoms or 2 elements, carbon and oxygen, there's nothing much to worry about, like asking yourself who is going to be placed in the middle, because there are only 2, carbon and oxygen. So draw them just in space like that, carbon and oxygen, and then ask yourself what's the contribution of carbon in terms of valent electrons, and what's the contribution of oxygen. Now you know carbon is in the 4th group of the periodic table, so definitely it should have a valency of 4. Or if you work it from atomic number, carbon has atomic number of 6. So if you write your electronic configuration is 1s2, 2s2, 2p2. So the outermost shell is the second shell. You sum up the electrons, is going to be 4, right? 2 plus 2 is 4. But as I say, the shortcut is just look at your periodic table and determine which main group element does carbon belong to? It's in the 4th group, so it should have 4 valence electrons because the number of valent electrons places an element in the periodic table. Oxygen is in group 6, main group 6, the periodic table, so it should have a valence of 6, or if you want, you can use its electronic configuration. Oxygen has atomic number of 8, so it's 1s2, 2s2, 2p4. Definitely the second shell has 6 electrons again. 2 plus 4 gives you 6. So you're looking at 10 valence electrons. So you want to spread, after the second step, you want to spread the 10 valence electrons around the atoms. But the first step that should be done is you trying to make the first bond in between here, between your carbon and oxygen, so that they just don't hang in space. So use 2 of the 10 electrons to make a bond. Now you're left with 8, right? You're left with 8 because you've used 2 out of the 10. So 10 minus 2 electrons, you get 8. And these 2 are the ones you just used to make a bond. So you need to spread the 8. But now from this step, how do you know how you're going to spread the electrons? Who do you give first? The answer is, out of these 2, oxygen is more electronegative than carbon because oxygen is further to your right of the periodic table. Electronegativity increases across the periodic table. So oxygen should receive the part of the 8 electrons before the carbon in a bid or in an effort to be octet. Right now, carbon has 2 electrons, oxygen has 2 electrons, they're shared, right? So to make the oxygen octet, it being electronegative, it should receive the electrons first before the carbon. So let's make the oxygen an octet by forcing it to hold 8 electrons. Right now it has 2 shared with the carbon. So 1, 2, 3, 4, 5, 6, 7, 8. Now you notice that all I've done is just to add 6 more electrons, right? So now the oxygen is in octet state. The carbon only has 2. Now out of the 10, so far we've used 8, right? So 2 are left. So the 2 that is left, we need to give carbon. Because remember, we have to spread the 10 electrons. Okay? So now it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the fact that there are 10, which is this structure that we just generated, the fact that there are 10 doesn't mean that the structure is complete, is completely correct. It's wrong, in fact, because anyway, you've satisfied the oxygen. The oxygen is in octet state. The oxygen has 8 electrons in its outermost shell. That's what you are going for, to make oxygen happy and stable. Give it a smiley face. But the carbon is not happy because, yes, you've spread around the 10 electrons, the 10 valence electrons, but the carbon is not in octet state. So we need to share some more electrons, sharing from oxygen. So that's what you are doing in step 4. Take one of the lone pair, bring it in between. That's how you make a double bond, because now you have 4 electrons. I told you 2 electrons make a bond. Okay. After transferring that lone pair, oxygen is still not happy. It has 6. 1, 2, 3, 4, 5, 6. The carbon is not happy, sorry, because it has 6 electrons. The oxygen is happy. It's still happy. No change. It has the 4 electrons shared and the 4 electrons outside, so it's still octet. So we need to transfer 1 more. That's what you are doing here. To make 6 electrons shared, which makes a triple bond. And you'll be left with a lone pair out and out. So that's the process of making it. It's tedious, but you need to practice. We're going to work some more. So right now here, carbon has 6 shared and 2 out, 2 lone pair, 2 and a lone pair, 2 electrons not shared, so it's octet. If you look at oxygen, it still has 6 shared and a lone pair which has 2 electrons, so it's still octet. Both of them are happy. So that's the correct Lewis structure for carbon monoxide. And that's, if you're to show the bonds, then This is it. So this structure up there is equivalent to this. So that will be the correct Lewis structure of carbon monoxide. So let's do some more examples. Alright, so for water, suppose you're not given this. Suppose you're just told to find the Lewis structure of H2O. Again, the first step is to draw your atoms looking for symmetry. And then determine the number of valence electrons available. So each hydrogen has one valent electron. So we're going to do 1 electron times 2 for each hydrogen. So the 2 hydrogens contribute 2 valence electrons. And the oxygen is in group 6. So you only have 1 oxygen, so it's 6 electrons. So generally you want to spread around 8 valent electrons, which are those. Okay, to do the steps for this, to determine the Lewis structure showing electrons, you want to at least form a bond between the 2 hydrogens. So far you've used 4 electrons out of the 8, okay? 8 minus 4, so you have 4 electrons to account for. Now remember the rule again for the hydrogens and halogens must be put out of the structure. That's why I put my hydrogens outside. Now the 4 extra electrons that are not accounted for in what we've done in step 1 will be put to the oxygen, because oxygen is more electronegative than hydrogen. Oxygens are found further to the right of the periodic table. So you're going to draw H, O, H, and this time give the 4 electrons to the oxygen. Now you see oxygen is happy, it's an octet, and the hydrogens are also happy, they are duets. Now remember, hydrogens can never be octets because a single hydrogen has 1 electron, electronic configuration 1s1. All it needs is 1 extra electron to become 1s2, which is a fully filled orbital, so we call that a duet state. You only have 2 types. You have the octet state, stability for the filled orbitals, outermost orbital, or the duet state stability for hydrogen or helium. Helium is a noble gas with the electronic configuration 1s2. So the Lewis structure of water, is going to be H, O, H, with oxygen having 2 lone pair of electrons. Now, this is how the model will look like, the ball and stick representation, where this is a hydrogen, that's a hydrogen, this is an oxygen. Now, I want to tell you that it's not going to be linear like this, the shape. We're going to talk about that in the next class. The shape is going to be bent because the 2 lone pair of electrons tend to repel with the two electrons in this bond, 2 electrons in this bond, because electrons are negatively charged, like charges repel. Now that forces these 2 bonds to warp, and you end up with a bent structure because these electrons here repel the electrons in the bonds. Okay, that's called valence shell electron pair repulsion theory. That's found, I think, a few slides from here. So I want you to try for HCl. Let me circle them. I want you to try for HCl and for ammonia and for methane by yourself. Let me work for you a set line, how you would work out the set line. Suppose you're asked to draw the Lewis structure for C2H2. Again, hydrogens, by rule, hydrogens should be outside. Right, so hydrogen should be outside. So we draw the hydrogens outside and the carbons are in the middle. And the other rule that is given for some of the structures, that the most electronegative element should go in the middle. Definitely here, carbon is more electronegative than hydrogen because carbon is farther to the right of the periodic table. Electronegativity increases across the periodic table. All right. So once you've done that for step 1, for step 2, you at least want to form a bond. Step 2, you at least want to form a bond. But before you form a bond, you want to determine the number of valence electrons. Okay, so let's determine the number of valence electrons. You have 2 carbons. Each carbon is bringing 4 valent electrons because a carbon is in the 4th periodic table. If you want, again, you can go by the electronic configuration: 2s2, 2p2. Carbon has 4 valence electrons, right? So it's gonna be 2 times 4 valence electrons, so you get 8 valent electrons from each carbon, and then you have 2 hydrogen. Each hydrogen is bringing 1 valent electron, so you have 2 electrons. The total valence electrons is 10 electrons to spread around the structure. So use part of these 10 electrons to make bond. So I'm going to use a red pen to at least make a bond in each. Now so far you've used 6 electrons out of the 10, so 10 minus 6 is 4 electrons unaccounted for. So again, how do you know where those electrons will go? You want to give those electrons first to the most electronegative element in your structure, and in this case you have the carbons. So we're going to draw our carbons and then give them the valence electrons. So I'm going to put 2 in each of the carbon because they are equally electronegative. Now at this point you want to inspect and see if the hydrogens are satisfied with the duet. Yes, correct. The hydrogens are happy with the duet because the hydrogens, the 1s2 is filled up, but the carbons are not happy. The carbons are sextets, right? The carbons are sextets. So you need to make the carbons happy, and the way to do that is to share. So I'm going to use a different color to show sharing. So let's share this one here. What do you end up with? You end up with a carbon Alright, so those electrons have been shared. So now if you look at this carbon here, is still a sextet, and this guy is still a sextet. So it's just the carbons are still not happy. So you need to do sharing again of the other lone pair of electron, right? Like that. So keep moving. You're trying to make sure that the carbon is an octet, so you end up with now 3 lone pair of electrons shared, and that makes the carbons happy, the hydrogens happy, because right now the carbon is an octet and that carbon is an octet, having the 6 shared electrons and the 2 shared electrons, and the hydrogens are duets. The hydrogens are duets, they're happy. Right, so that's the answer. So the Lewis structure for acetylene, which is an alkyne, we'll talk about that in chapter 4, is gonna be HCCH, which is equivalent to HC with a triple bond because you have 6 electrons shared. And this is also same as H a bond C, triple bond C, a bond H. No unpaired electrons, no unbonded electrons. Okay. So that's the structure. This is just the same as C, 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 H. You have a carbon here and a carbon there, which is this carbon and this carbon. And again, I showed you how you get that. Now I want you to do the same concept and find how you would work out the Lewis structure of ethene, where there is a carbon here and here. And also find how this was obtained by drawing the Lewis structure. So that's your homework. So I'm going to show you an example of how to get the Lewis structure for formaldehyde, which is this guy. So how do we get this structure? By working out our formula. So I'm going to work it out on the whiteboard. So if you're asked to draw the Lewis structure of that guy, which is just formaldehyde, follow the steps again. Now remember, I told you that you might want to put the most electronegative element in the middle. It's not going to apply here. Okay, so the right way to do it is to put hydrogens out and the oxygen out, because if you put oxygen in the middle, you're going to be stuck somewhere with the process. That's how you know that you did the wrong thing. Okay. Alright, so that's the first step. At least have some symmetry. Let's put carbon in the middle and then oxygen outside. As I said, you don't want to do this. You're going to be stuck somewhere with your spreading the electrons. This won't work. If you want to try, you see, you're going to be stuck spreading your electrons. So this is the correct drawing. This is the wrong placement of elements in space. Now let's determine the number of valence electrons. And of course, oxygen is in group 6. It's going to give you 6 electrons. You only have one carbon, it's group 4, 1 electron. Hydrogens, there are 2 of them. It's going to give you 2 electrons because it's 2 times 1 valent electrons. Total, you have 12 electrons to spread. So start by at least forming a bond in each. Okay, that's what we've done. But now you only used 6 electrons. So 12 minus 6, you have 6 electrons unaccounted for. Where will these 6 electrons go? They will first be given to the most electronegative element in the structure. In this case, it's going to be oxygen. Force it to be an octet. Right now it's an octet. You have 6 electrons to the outside and 2 electrons shared. 6 plus 2 is 8. So the oxygen right now is happy. But the carbon is not happy. See, the carbon is not happy. Carbon right now is a sextet. So to make it happy, you really want to transfer a lone pair in between there. And what will you end up with? You're going to end up with this structure with a hydrogen. Hydrogens are happy, they are duets. And then 4 electrons shared. And then since you move this lone pair in between, you're left with 4 electrons to the outside. 4 electrons to the outside. Alright, and then now at that point again, inspect and check and see if everyone is happy. Of course, hydrogen is happy because it's a duet. So it's this hydrogen, it's happy, it's a duet. The 1s2 is fully filled, the outermost shell is fully filled. And then the oxygen is happy. There's 8 electrons around it, so it's an octet. And the carbon is happy too. I'm going to circle it with a different color code, the blue color code. The carbon is happy. It's an octet too, so it's also happy. So give it a happy face. So that tells you this structure, that where we are right now, is the correct Lewis structure for formaldehyde. And I told you each bond is formed by 2 electrons. So between carbon and oxygen, you have a double bond and you have 2 unbonded electrons. We have 4 unbonded electrons, or 2 lone pairs. They are lone pairs because they are lonely, they are not bonded. And the hydrogen is there and the hydrogen is there, and that's the answer. Alright, I think so far you got the concept right, okay? You got the concept right. You just have to practice. So I'm going to stop here. This is the lesson we would have had today. I'm going to stop here. Whenever we meet, we're going to do the Lewis structure of a charged species. So I'll help you remember what I've just explained here and then draw the Lewis structure of ammonium ion. Okay? Ammonium ion is NH4+, so we're going to determine why that plus is there. So we'll move from here in the next class.